hang this one. Let's talk about bonding. Everybody's favorite unit. Bonding. All right. There were 3 types of bonding that we talked about this year. We talked about ionic, covalent or molecular, and metallic. There's only one thing you need to know about metallic bonding. First of all, it's a metal. Second of all, they're positive cores in a sea of mobile electrons. Remember that metals lose their electrons. They have positive oxidation states, which means they lose electrons. Okay, so that's what makes a metal a metal. That's why they have luster. That's why they're malleable. That's why they conduct electricity. So you have these positive cores, these nuclei and kernel electrons that donate their valence electrons to the greater good, okay, the sea that they're in, and they move around. That's why when you add a battery, metals conduct electricity as a solid. A metallic crystal is a metal. It's just a metal. So as Mr. Delo says to his classes, pick the freaking metal. If they ask you which is the metallic crystal, which one has metallic bonding, pick the metal. Remember, it's to the left of the staircase. All right. Ionic bonding. The biggest thing you need to remember about ionic bonding is it's a transfer of electrons from metal to nonmetal. The metal gives up its electrons, it has a positive oxidation state. The nonmetal takes the electrons, okay? The electronegativity difference, that means the difference between how hard they pull on other atoms' electrons has got to be greater than 1.7. That means there's a big difference in strength. That would be like one of you playing tug of war with a little first grader. You would win. You would probably rip their arm off. Okay, maybe not that violent, but you would take the electron. You would win the game, okay? So the metal becomes positive and transfers its electrons to the nonmetal, which becomes negative. They stick together because of this charge, this difference in charge. Positives and negatives are attracted to each other. They form lattices, okay? A solid ionic crystal forms a crystal lattice where you have positives and negatives opposite attracted to each other. If you add water to it, plus H2O, it dissolves, and these positives and negatives are free to float around. When they're free to float around, they conduct electricity. So ionic solids conduct electricity when liquid or aqueous. What else do you need to know about ionics? They have high melting points and high boiling points. When you think about ionic solids, please think about salt, table salt, okay? It's got a high melting point and a high boiling point. I'm sure that your mother has never burned salt, okay? You can burn sugar, but sugar is covalent, so it's got a lower melting point, okay? High melting points, high boiling points, and they conduct electricity when liquid or aqueous. The Regents loves asking about ionic compounds, okay? They love asking about properties of ionic solids. Those are really important that you know them. Know that there are transfer of electrons. Have an example of them. Your example, like I said, is NaCl. Covalent bonding is where it gets a lot more complicated, where we get shapes and where we get polar versus nonpolar, bond polarity, molecule polarity. What you need to know about covalent bonding is it's 2 nonmetals. Maybe I'll use a different color. This one's kind of boring me now. Let's use green. 2 nonmetals, okay? If it starts with a carbon, it's covalently bonded. Okay, so if it starts with a CH3, it's organic. Remember that organic molecules are covalently bonded. 2 nonmetals, they share. This is happy, okay? Sharing is caring. They share electrons. Their electronegativity difference, that's the difference in their electronegativities, how hard they pull on each other's electrons, has got to be less than or equal to 1.7. If the END is 0, it is a non-polar bond. Okay? okay? It is a nonpolar bond. The two little atoms are sharing the electrons equally. A great example of this is O2. Here are my two oxygens, okay? Each oxygen has 6 valence electrons. All right, here's their valence electrons. You can see that O2 has a double bond. It shares 2 pairs of electrons. The END between oxygen and oxygen is 3.5 minus 3.5, so it is 0. Okay, so this is a nonpolar bond. It's also a nonpolar molecule because it has symmetry. Okay, it's symmetrical any way you slice it, basically. Okay, three-dimensional. Remember, we're thinking three-dimensional, but we can only draw in 2 dimensions. If it's symmetrical molecule, the molecule is non-polar. That means it has really weak intermolecular forces, it doesn't behave like a magnet, and the charge is evenly distributed across the entire molecule. Okay, more on covalent. So we talked about nonpolar bonds having an electronegativity difference of 0. If the END is greater than 0, okay, but it's also less than or equal to 1.7, and I realize I should have drawn that the other way, it is a polar bond. An example of something with a polar bond is H2O. When I'm talking about the bond polarity, I'm talking about a little slash, this little dash here, the line, not the whole molecule, just the bond between hydrogen and oxygen, okay? Oxygen has an electronegativity of 3.5 from table S. Hydrogen has about 2.2, okay? The difference there is about 1.3. This is a polar bond. Ionic bonds are not polar, they're ionic. Okay, so covalent is the only one that's split between polar and nonpolar. We have a polar bond. The one that has the higher electronegativity, I'll write that whole thing out, is stronger. So he's going to get the electron more and become partially negative. That partial delta means partially negative. If it has a lower one, I'm going to use the quotes there so I don't write electronegativity again, it becomes partially positive, okay? So here, oxygen, I'll write this in red so you can see it, is partially negative because it's stronger, and hydrogen becomes partially positive, okay? The same thing is true for this bond between oxygen and hydrogen, where oxygen becomes partially negative and hydrogen becomes partially positive. Now we look at this molecule to determine if the overall molecule, the net of these two dipoles, the net of these two polar bonds, is polar. Well, water is polar. If you remember nothing else from this video, remember that water is polar. Water is polar. Here's my line. I've got positives on one side and negatives on the other. That makes water a dipole. That means it's a polar molecule. It's got a negative end and a positive end, okay? It is asymmetrical. Asymmetrical, polar, symmetrical, nonpolar. Okay? Now, how do you figure out the shape of a molecule? I'll tell you the regents will ask you easy ones. The best way to remember that is based on the group. Okay? So this is the group in the periodic table. We're talking about the central atom. So group 14, 15, 16, 17. These are the 3 that you really need to know. We'll talk about 13 but down here. Group 14, your example here is carbon. Okay? Carbon forms a tetra. Let me move this. Woo. Okay. Carbon forms a tetrahedral molecule. Unless it's making multiple bonds, okay? The exception to that is CO2. CO2 is linear. Draw it. If you aren't sure what shape, draw it. Carbon is generally nonpolar unless if it's bonded to all 4 of the same thing. If it's bonded to something different, like if this was CH3Cl, this is now polar because it lost its symmetry. Okay? If that Cl went away and it was CH4, like our favorite methane, this becomes non-polar because it's even. Okay? The charge is equally distributed. It is tetrahedral and it is evenly distributed. Okay? It is symmetrical. Group 15, your nitrogen. Okay? This is pyramidal. I spelled it wrong. Forgive me. Okay? This is always polar. Group 16, oxygen. Okay? Oxygen, sulfur, selenium, tellurium, etc. Everything in group 16 on the periodic table is bent. Guess what? Polar, always, because of those lone pairs of electrons. Group 17, we're looking at fluorine. Okay? This is linear. It can only make one bond. It is polar if they're different things. Non-polar if they're the same. That means if it's F2, it's non-polar. If it's HF, it's polar. Okay? Bonded to something other than itself or other than something that has the same electronegativity, it's going to be non-polar. Otherwise, if it's bonded to itself, it's non-polar because it is symmetrical. Okay? Group 13 are your exceptions. Okay, this is like aluminum, boron. Okay, that's a B, boron, excuse me. Aluminum and boron, they form trigonal planar. Okay. Group 14 makes 4 bonds. Group 15 makes 3. Group 16 makes 2. And group 17 makes 1. Group 17 has 7 valence electrons. They only need 1 more to be happy to get that perfect 8. Group 16 has 6 valence electrons, so they only need 2 more, so they need to make 2 bonds. They can certainly make those 2 bonds to the same atom. In the case of O2, has a double bond, okay? Group 15 makes 3 bonds. Nitrogen has 5 valence electrons. It needs to gain 3. N2 has a triple bond. Because nitrogen bonded to nitrogen, they have to share 3 pairs of electrons for everybody to have 8 and be happy. Group 14 is carbon. Organic chemistry is our carbon chemistry, so think about that. Carbon makes 4 bonds, always. Hydrogen makes only 1. Okay? That's all of your good stuff about covalent bonding. You do not need to know the shapes as much as you need to know the polarity versus non-polarity. Be able to recognize a symmetrical molecule is nonpolar and an asymmetrical molecule is polar. Non-polar. Okay? If it has lone pairs of electrons, as long as they are not exactly the same as the lone pairs of electrons on the other side, in the case of F2, for example, it is polar. Okay? If there's here is a case with lone pairs where it's nonpolar. This is nonpolar because it's the same, okay? It's perfectly symmetrical. However, if it has lone pairs like NH3, like ammonia, it's going to be polar. All right, great.